In this lesson, we're going to take a look at series and parallel circuits, how current flows in each one of them, and how to calculate the equivalent resistance in them, which actually is going to allow us to figure out how much current is flowing in the circuit. So we'll start with series. We've basically looked at series circuits in this class so far because we've only looked at a circuit with one thing in it. Now we're going to look at a circuit with more than one thing in it. Now we could go to 3, 4, 5, 6, but I think we're going to limit ourselves to just two circuit elements plus the battery. So current leaves the battery, and in a series circuit there's only one path for it to flow. So we'll go through that resistor, which we'll creatively call R1, and we'll come through this resistor, which we'll call R2. So here's R1, here's R2. And we're going to go ahead and we're going to say, hey, this resistor is equal to 20 ohms, and this resistor right here is equal to 4 ohms, and we're going to let the voltage of the battery be 48 volts. Okay? Now the question is, how much current flows in this circuit? And the answer is, well, normally we would say V equals IR, right? V equals IR, and we would use Ohm's law. But the question is, which one of those resistances do we use to figure out the current? And the answer is we have to use a combination. We have to actually account for all of the resistances. Now when I add resistors in series like this, I am making it harder for current to flow. Now the current here is everywhere the same. Current is everywhere the same. And the reason for that is there is only one path. Whatever current comes through here, we'll say it's I, goes through this resistor, it's still I, because everything that goes into that has to come out of that. Charge cannot be created or destroyed. Charge is conserved. And so that current is still flowing through here, I, and it comes back around in I. And so the same current is everywhere in this circuit the same. However, the energy or voltage, energy per charge, is not the same. This battery's job is to increase the energy per charge of the current in the circuit. And so it pulls electrons here, does some work on them, increases their energy, and shoves them through here. Now this resistor takes some of that electrical energy and converts it into heat, which means there's less electrical energy over here, less energy per unit charge coming out. So across R1 we get a voltage drop. So we have a voltage drop across R1, and we have a voltage drop across R2. We call those V1 and V2 because we're creative like that. So the voltage drop across R1 plus the voltage drop across R2, those have to be equal to the total voltage supplied by the battery, because energy cannot be created or destroyed. And since the current is the same, then the sum of the voltage times current equals the voltage times current. Now what this means is the battery has, well, the resistance of the circuit, the total resistance, what I'm going to call RT, is the voltage of the battery times the current. Well, this is equal to the current times whatever R2 is, and this is equal to the current times whatever R1 is. And so I can still add these up and get that. And so what I see is R1 plus R2, I'm going to pull that I out, equals I times the total resistance, sometimes called equivalent resistance of the circuit. Well, I's everywhere, so I can divide it out of that, and I see that the total resistance of this circuit is given by R1 plus R2, and that's because it's a series circuit where everywhere current is the same. So I can apply Ohm's law to this, and I can say, well, I've got 48 volts of potential, and this is equal to the current times the resistance, and instead of 20 ohms or 4 ohms, I'm going to use 20 plus 4 or 24 ohms, divide both sides by 24, and I can see that in fact the current in this circuit is 2 amps. Okay? So on a series circuit, one path, that's what series means, there's one path for the circuit to flow, and the current is everywhere the same, and because of that, to find the equivalent resistance or the total resistance of the series circuit, all we have to do is add up the individual resistors.